Good afternoon. My name is Jonathan Sessler, and I'm a chemistry professor here at the University of Texas at Austin. And I'm going to try and tell you a story. It's a personal story, but it's also a drug development story. And it goes way back to when I was much younger and better looking. I won't say I was good looking, but better looking. And the story has two or three themes that intertwine to lead to a tale of what it takes to try, fail, and try again at drug development for cancer. The peroration of this talk will lead to efforts to develop platinum using Texiferin as a specific carrier to overcome resistance. But before we get to that, I want to wind all the way back and start at one of the two beginnings leading to this story. So this goes to when, maybe a long time ago, because I've had the privilege of being here on the faculty for many, many years. But in 1984, when I was 28 years old, I came here. I had done my education, undergraduate, at Berkeley, graduate work at Stanford, also in the Bay Area. Then I worked for postdoc, so this is after one's PhD, with a soon-to-be, but not yet, Nobel Prize winner named Jean-Marie Lehn in France. And then I did a further half a year or so of additional study in Kyoto, Japan, and that was a delightful cultural center. And I must have been one of the few people who showed up in Austin, Texas in late August and thought it was cool compared to the heat and humidity of Kyoto, Japan. While doing my PhD with the famous Jim Coleman, supervising professor at Stanford, and then also studying in France and in Japan, I had worked on a class of compounds called porphyrin. And that's shown on this slide as the first chemical picture. And a porphyrin, if you're not a scientist, or even if you're a scientist and not an organic chemist, you may not know this name unless you're unfortunate and have one of the rare diseases associated with poor metabolism called porphyria. You may have never heard of this, but you have seen it. And that red color comes from porphyrin. It's the ring that holds the iron to make heme that goes into hemoglobin, which carries oxygen around in your body. And porphyrin has many other functions for electron transfer, for catalysis, and no fewer than 4 Nobel Prizes have been awarded to porphyrins. So I thought it would be fun to continue studies of these molecules. But I quickly realized that in Texas, things are different from in other places. And on this part of the slide, you can see two major influences. One, on the right-hand side of the slide, you can see the famous Lone Star of Texas. But notice up close, the Star of Texas has 5 points to it. And if you go back to porphyrin and you look at it carefully, you see Ns. That stands for the element nitrogen. And if we count, we see 4. But in Texas, it better be 5. So this is a disconnect. The other thing you see on this slide are longhorns. And I came to Texas and I thought, wow, animals here in Texas are bigger than they are back where I grew up in California. We had little squirrels, but we didn't have longhorns. And it occurred to me that in Texas, things should be bigger. And it turns out that's an animating philosophy in Texas. Things should be bigger, and we're proud here at the University of Texas that they're often better as well. So if you map this set of influences into porphyrin chemistry, you come, as I do, to the next concept, which is the idea that you should make not a porphyrin, but a texaphirin, which would be a Texas-sized porphyrin. And so we set out to do that. And as a young faculty member, the rank is called assistant professor. And that is not a permanent position. You have 5 or 6 years to prove yourself to the world, and it really is world-class chemistry that you must do if you're going to become part of the permanent staff at the University of Texas. And that's appropriate, but it's challenging. And my thought was a very simple one. If I made a molecule and named it after the state, it would be very difficult to deny me tenure. And I'm pleased to report that that experiment was successful. So that led to this new molecule, maybe 20% bigger than the porphyrins you'd find north of the Red River. So we had succeeded in the basic chemistry. And we quickly found out, as you can see from this technical slide, which shows something called a cyclic voltammogram, which tells you how electrons go in and out of molecules. We found, in contrast to what's true for typical Yankee-sized porphyrins, that the Texas porphyrin, or texaphirin, captured electrons a lot easier. Once it captures electrons, it will hand the electrons off to oxygen. Oxygen, as we know, will take electrons. That's the basic process of burning. But normally, it is very slow. It's what chemists call kinetically inhibited, unless you activate the oxygen. Typically, we do that with a match when we are lucky enough to enjoy this lovely weather and stoke up the coals and have a nice barbecue. But you can also do it with light, and here we're doing it with chemistry. So we take oxygen, take an electron from the reduced or electron captured version of texaphirin, and that makes a radical species called superoxide. That goes on and does many things. Disproportionates to make hydrogen peroxide, but all these daughter products and the original radical or reactive species, superoxide, these are cancer-killing agents. They'll kill other cells as well, but cancer is more susceptible. So the idea is, with a molecule that's easy to catch an electron, it should be able to do that from any of the metabolites or some of the metabolites in your bloodstream, produce these reactive forms of oxygen, and kill cancer. If you take that heme out of the hemoglobin that's in your blood and purify it and re-inject it, it will localize to cancers. This has been known since World War II. German chemists, back in those days when you made something new, it was traditional to test it on yourself. And from people in Meyerbett's World War I era on, Figge, World War II, this was done. We knew then that a porphyrin would go to cancer. We knew that the texaphirin would give this active form of oxygen. Maybe if we were lucky, the texaphirin would model the normal porphyrin, go to cancer, and now produce this killing agent. So that was the idea. And so then we decided that we could take texaphirin and try and cure cancer.